Hi, welcome to Competitive Cracker. So, in this video, we will be discussing about singularities in mathematical physics, complex analysis. You know, complex analysis is of a very great importance in CSIR examination point of view. And in that complex analysis, you will be asked to check whether a function is analytic or not. Checking the analyticity and all, it is very simple, but they will be giving some unknowns, and they will be asking you to find the values of unknowns if the given function is analytic or not. Then Lorentz expansion comes. Then there are different applications of this analytic function properties. There are many properties for these analytic functions, and you know what are these properties and how they are being calculated. So, the analytic functions has many properties. If f of z is equal to u plus iv, then u and v are they are two curves with perpendicular slopes. That all you know, that we all have we already have discussed about that in the differential equations. In the continuation of that, we will also discuss that in the complex analysis. It is also very important, and based on that, if u is given, we should be able to find v, and if v is given, we should be able to find the real part of that u. And also if either a real part or imaginary part of that function is given, we should make them grow to find out f of z, and many applications are there, and we all have discussed in our classes. And in this video we will discuss about the singularities and its properties. Okay, so let us start discussing about singularities. So, what are these singularities? Singularities. See, I have a domain. See, this is my domain, and there are many function points in this domain. Okay, there are many function points in this domain. So, this is my domain. This is my domain in which the function, the complex function f of z is valid. I have some arbitrary complex function f of z, and this complex function is valid in this domain. So, that means this is valid means f of z is analytic. F of z is analytic in the domain, inside the domain. F of z is analytic inside the domain. So, that is a peculiarity. So, f of z is analytic means f of z is valid means it is the function is analytic inside the domain. Then what is the meaning of that analyticity? If the function is analytic, that means f of z is continuous and differentiable at every point inside the contour or domain. So, inside this contour, the function is analytic. That means it is continuous. The function is continuous and is differentiable. That means the function is continuous. The function is continuous and differentiable. The function is continuous and differentiable inside the domain, inside the contour. Inside the contour. Contour means this boundary. Okay. So, this continuity, the function is continuous. The function is continuous means if we have a particular point z is equal to a, towards the left and towards the right of that point, the function will be continuous. Clear? That means limit z tends to a minus f of z0 will be equal to f of z. Let it be f of z. F of z will be equal to limit z tends to a plus f of z. So, the function is continuous towards the left and towards the right of that particular point. That is the continuity. And differentiability, the function is differentiable So differentiability means limit z tends to, or z0 tends to some z0 tends to some 0, z0 tends to 0, then what it will be? F of z minus z0 minus f of z by f of z minus z0 minus f of z divided by z0, f of z0, correct. So f of z minus z0 minus f of z plus z0 by z0, which means this is d f of z by dz, df of z by dz. So that is the differentiability. This continuity and differentiability, these two properties are combined together to get CR conditions, Cauchy-Riemann conditions, that you know. That means inside this domain, Cauchy-Riemann conditions is also valid. Okay, so then only the function will be analytic, right? So I have this domain, and in this domain a function f of z is valid. The function f of z is valid means it is analytic. It is analytic means the Cauchy-Riemann conditions are satisfied inside this contour. So when Cauchy-Riemann conditions are satisfied, the function will be continuous and the function will be differentiable inside the contour. So that is the meaning that the function is valid inside a contour. Clear? So if that is the case, and see, I have a contour like this, and I have a particular point, some z is equal to a. I have a particular point, some z is equal to a, and consider the function f of z is equal to some z square divided by z minus a. Some z square divided by some z minus a. If you substitute the value of z is equal to a minus a is 0 and 1 by 0 or something by 0 is infinity. It is not defined, right? It is not defined. That means the function is the function f of z. The function f of z is not well defined. The function f of z is not well defined at the point z is equal to a. So z is equal to a is a particular point at which the function f of z is not well defined, and in all other portions or in all other area inside the contour the function is well defined, except at a particular point z is equal to a. So at z is equal to a there is some peculiarity, and what is that peculiarity called? And that peculiarity, that means f of z is not analytic. Is not well defined means it is not analytic. F of z is not analytic at z is equal to a. The function f of z is not analytic at z is equal to a. So that peculiar point at which the function is not analytic is called singularity. Clear? So that here in this context here z is equal to a is called a singular point. Z is equal to a is called a singular point. It's called a singular point. Clear? So at this point z is equal to a is called a singular point. So to find the singular point, if you are given a complex function like this, complex function f of z, to find a singular point, to find a singular point, very very important. To find a singular point, you need not worry, just substitute the denominator is equal to 0. Just substitute the denominator of the given function is equal to 0. Here z minus a is equal to 0, then z is equal to a will be a singular point. So singular point is that point at which the denominator is equal to 0. The denominator is equal to 0, the function becomes undefined at that particular point. So when you substitute denominator is equal to 0, you will get z is equal to some point, and that point will be the singular point. Clear? So that is the singular point. So this singular point, then we will get some singular point. There may be some z is equal to some 1 or 2 or 3 singular points will be there, and all these singular points, all these are singular points, but also these singular points are also called, they are also called poles. All singular points are also called, the singular points are also called poles. Not all singular points. Singular points are also called poles. And what are these poles? Let us discuss. See, they are also called poles. That means the singular points inside the domain. The singular points inside the domain. Singular points inside the domain in which the function. The singular points inside the domain in which the function is defined. The function is defined. Is called poles. Is known as poles. Are known as poles. So the singular points inside the domain in which the function is defined are known as poles. So all these singular points are essentially the poles itself, but there are some differences that I will sort it out. See, then therefore all singular points need not be poles. Why? All singular points need not be poles. Why? Because if you substitute denominator is equal to 0, you will get many singular points, and some singular points will be outside the domain. Some singular points, there are chances that there are some singular points which will be outside the contour. Okay. So there are some singular points which will be outside the contour. Are we required to think about that? No. They are singular points, but they are not poles. So the singular points which are inside the contour, the singular points which are inside the contour are known as poles. All poles are singular points, but all singular points need not be poles. Clear? So all singular points need not be poles, but all poles are singular points. But all poles are singular points. All poles are singular points. Very, very important. Okay. So we may get singular points which are outside the contour. So we should concentrate only on those singular points which are inside the contour. Why? Because the function is well defined only inside the contour. We don't know the behavior of the function outside the contour. So all singular points need not be poles, but all poles are singular points. Clear? So let us make it more clear. So singular point. So in short, a singular point is that point at which the function, the singular point is that point at which the function f of z is not analytic. Is that point at which the function f of z is not analytic. And poles, they are the singular points. They are the singular points inside the domain. They are singular points inside the domain in which in which the function is defined. The function is defined. Let it be the function is well defined, then it will be more meaningful. The function is well defined. Clear? So that is the difference between a singular point and poles. Is it clear? Then when you read across these singular points, you may come across this term, isolated singular points. Isolated singular points. What are these isolated singular points? As the name itself suggests, when there are no singular points in the vicinity of the singular point which we have defined, then that will be the isolated singular point. So if there are no other singular points, if there are no other singular points, if there are no other singular points in the vicinity of the singular point which we have defined, that means Z is equal to A here. If there are no other singular points in the vicinity of, or you may come across this word neighborhood. The neighborhood of Z is equal to A, which is our singular point, then it is called an isolated singular point. Then it is called an isolated singular point. It is called an isolated singular point. Clear? So, for example, if you consider the function f of z is equal to some z by some z minus 1 into some z minus 2. So what are the singular points? To find the singular points, we substitute the denominator is equal to 0. That means z minus 1 into z minus 2 is equal to 0. So z minus 1 is equal to 0 implies z is equal to 1, and z minus 2 is equal to 0 implies z is equal to 2. So these are the singular points, and are there any other singular points? No, there are no other singular points in the vicinity of 1 and 2, and they are each one of them are isolated singular points. Is it clear? So there are no other singular points in the vicinity of z is equal to 1 and z is equal to 2. Okay, so that's how they are singular points, and they are classified as isolated singular points. Clear? So this when you study this singular points and singularities, there are different types of singularities. Types of singularities. Types of singularities. See, here I consider let z is equal to some a be a singular point. Be a singular point. Z is equal to a be a singular point, and let it be some isolated one also. So I have f of z is equal to summation n is equal to 0 to infinity an into z minus a whole power n plus summation over n equal to here 1 to infinity. Please keep in mind n is equal to 1 to infinity bn z minus a whole power minus n. Z minus a whole power minus n. So this is my function, and this function has z minus a whole power n plus z minus a whole power minus n also. That means z power n, here z power n will be in the numerator, and here z power n will be in the denominator. So that means an analytic function will have two parts. You will sum of two parts. and this part, the first part is called an analytic part. The first part is called analytic part, and the second part is called the principal part. What part? Principal part. So the first part is the analytic part, in which Z power, the powers of Z will be in the numerator, and the principal part means the powers of Z will be in the denominator. Clear? So let us discuss about the singularities. See, first singularity that I am discussing is about essential singularity. First singularity is essential singularity. Essential singularity. See, this is a essential singularity. What kind of a singularity is that? See, essential singularity means if the principal part contains infinite number of terms. Infinite number of terms. If the principal part contains, if this part contains infinite number of terms, then it will be called an essential singularity. Clear? So, as an example, let f of z be equal to some e power 1 by z. F of z is equal to e power 1 by z. If you expand this, what is the expansion of e power 1 by z? It is 1 plus 1 by z plus 1 by 2 factorial into 1 by z square plus 1 by 3 factorial into 1 by z cube plus etc. See, all the powers of z are in the denominator. That means it is the principal part. It does not have any analytic part. It has infinite number of terms in the principal part. Clear? So that means e power f of z equals e power 1 by z has an essential singularity. It has an essential singularity. It has an essential singularity. It has an essential singularity. So what is the essential singularity of here it should have essential singularity means the function must be undefined. The function must be undefined. To make e power 1 by z undefined, what should be the value of z? What should be the value of z? If z is equal to 0, 1 by 0 is undefined. So e power undefined is also undefined. So essential singularity at z is equal to 0. The point of essential singularity is z is equal to 0 for e power 1 by z. Clear? So that is the essential singularity. That means it only has infinite number of terms in its principal part. And then we have another singularity called pole of order. This is a pole of order. So the pole of order, what does that mean? It contains the principal part contains, if the principal part contains finite number of terms. So in the essential singularity, the principal part contained infinite number of terms, and in the pole of order, the principal part contains only finite number of terms. Then it is called a pole of order, singularity, or it is of a pole of order. Then example, when you see an example, then it will be more clear. Example, f of z equals some z by z minus 1 into z minus 3 whole square. Z by z minus 1 into z minus 3 whole square. How to find the singular points? Singular points has to be found out by substituting the denominator is equal to 0. When you substitute the denominator is equal to 0, z minus 1 will be equal to 0. So, z is equal to 1, and then you substitute z minus 3 whole square is equal to 0, then z is equal to 3. But the order of this pole and order of this pole is different. Z is equal to 1 is a pole of order 1, is a pole of order. It's a pole of order 1. And what is this? It is a pole of order. It is a pole of order 2. Pole of order 2. It's a pole of order 1 and it's a pole of order 2. See, the power is 1 here, the power is 2 here. Clear? So, that is it is a pole of order 2 and it's a pole of order 1. So, pole of order 1 is called a simple pole. Pole of order 1. Pole of order 1 is termed as a simple pole. Is termed as a simple pole. So, this is how we consider we consider poles, and this is how we assign order to each and every poles. Clear? So, if we need to have a pole of order, then the principal part of that function should contain only finite number of terms. Clear? And the third one which we are discussing is regarding removable singularity. Removable singularity. What is this removable singularity? See, here the principal part contained infinite number of terms, here the principal part contained finite number of terms, and then what will be a removable singularity? The principal part contained not term. So, if the principal part contain not term, the principal part contain not term, or the principal part is absent, or the principal part is absent, the expansion the principal part is absent, then that is called a removable singularity. Is it clear? So, example, if you consider the function f of z equals sin z by z, sin z by z. If it is the if this is the case, you can expand it. F of z equals 1 by z into 1 by z. What is the expansion of sin z? It is z minus z cube by 3 factorial plus z power 5 by 5 factorial minus etc. If you take this z inside, then f of z will be 1 minus z square by 3 factorial plus z power 4 by 5 factorial minus etc. So, that means there is no principal part. All the powers of z are in the numerator. Principal part is absent. So, it is called a removable singularity. Clear? So, I hope you have understood these singularities and types of singularities, what are poles, what is the order of a pole, and how a pole is determined, and what are the differences between a singularity and a pole. Is it clear? So, I hope it is very clear to you, and more problems are given in our app. So, the more details about these singularities, branch points, and all the other details are being uploaded in our app, and please stay tuned to the classes in our competitive cracker app. So, it is my humble request for you to study these singularities, because these singularities and how to find these singularities, they are of great importance in solving complex integrations. Complex integrations are of very great importance in our each and every competitive exams, even for set exams in different states. Okay, these complex integrations. Complex integration is not of a single type. There are 5 or 6 types of complex integrations are there, and they are of great importance. Okay, so you should study it very well. Then only you will be able to solve different types of questions that they may give you. So the basic thing that you need to study all those complex integration is about learning about these singularities and poles and such other things. So so please go through our classes. There are many tips and there are many tricks to solve those complex integrations, which are exclusively available only in our app. So please stay tuned to that. Okay. So I hope you have understood this. And so competitive cracker is one of the leading forerunners, forerunner in one of the forerunner in all the competitive exams. And we have launched our CSIR NET physics course, and we have many highlights to our course, which we have been following for our various competitive exams. Okay, for CAT, SET and such other and all other competitive exams, especially in we are forerunners in all these teacher eligibility tests. So I think competitive cracker can definitely lead in CSIR NET physics also, and we have studio recorded classes which will be available in our app, and we will complete or we will cover all the syllabus, and no other coaching centers will be covering the entire syllabus. So we will cover the entire syllabus, each and every subtopics will be covered. Okay, so other coaching centers will be focusing on their focus area or their strengths, and they will be completely ignoring the other parts. We will not be doing that. We will cover each and every subtopics, and we will go through each and every subtopics, and we will teach you. Okay, and we have special live sessions. Our recorded classes will be many recorded classes will be there for each for quantum mechanics itself. You may get some 70 or 100 recorded classes, and in spite of that, you will be given special live sessions also for solving additional questions, and for making you to explore more, or to making you for more for giving you more challenges, and for our discussions for. Okay, then we have complete study materials will be provided, PDF notes will be available, and we have 24/7 doubt clearance system. Please do not get mistaken by the live sessions are for doubt clearances. No, these live sessions are for giving you more opportunities to solve more problems and to discuss more problems. And there also you can ask doubts, no problem. But doubt clear, you can have a 24/7 doubt clearance. You can contact me, or you can contact your mentor, and you can get your doubts solved immediately. Clear? And we can you people can learn through our app and our website, and this CSIR examination is not on paper, right? So it is not on paper. It is in you will be given a computer based screen, and it is a computer based test, CBT. So for getting that coaching, you can have in-app examinations for each subtopic. For each subtopic you will be given exams, and weekly exams will be given, and in addition to that weekly exams, you will be given some 7 or 8 mock tests also before going for CSIR examinations. So with that only you will be allowed to go for the final examinations, where you can give your maximum and get maximum results. Okay, so also we will be discussing previous year question papers, and which will be very helpful for you for your journey. So this is our system, and we will be following this, and I request you all to join us, and we will study together. I do not claim that we know everything. We are greater than every others. No, we will not be claiming that. We claim that we will grow and we will study together. So I welcome you all to Competitive Cracker, so that we can excel. Bye bye. Thank you.